Welcome back to this second part on muscle contraction. So let's get going to take a look at how these muscles actually contract using their thick and thin filaments. So the model by which muscle contraction occurs is based on something called the sliding filament model, and this was presented the first time, I think, sometimes in the 1950s. I'm not entirely sure. But according to the model, muscle contraction is due to the thin filaments sliding past the thick filaments into the spaces that are left between the ends of the thin filaments in each half of the sarcomere. So we can pull this side into the middle and this side into the middle, and that will move the Z line closer over here and this Z line closer over here. And when the same thing happens over here, the I band will contract. So we'll see contraction of the I band and contraction of the sarcomere, as well as the A band. Well, the A band probably won't change at all. So the thin filaments are going to slide into this space here between the thick filaments. So the amount of force generated here depends on the number of acting binding domains that are on the thick filament. So the more myosin heads you have in there, the stronger the contraction of the muscle will be. So the sliding of the thin filaments past the thick filaments depends on the elaborate structure of the sarcomere, and as we'll see in a moment, the myosin protein is going to use the energy that is released when ADP is hydrolyzed and the phosphate is transferred around within the motor's head domain. So the regions of overlap between the thick and the thin filaments are characterized by the presence of these transient cross-bridge structures. So the cross-bridges are formed from links between the F-actin of the thin filaments and the myosin heads of the thick filaments. And so these are transient interactions between the head of the myosin that's going to do the work and the actin in the thin filament. So there's going to be this constant association and dissociation, and there's going to be the cocking of the head and then the movement of the thin filament by elastic energy that's stored in the myosin head domain. And so the overall result of that is that the sarcomere will shorten, and that will result in muscle contraction. So we've got to explain how we get this repeating cycle of cross-bridge formation and then cross-bridge release. And the driving force of the cross-bridge formation is going to be the hydrolysis of ATP. So let's take a look at this mechanism of muscle contraction and focus on the cross-bridge formation and the cross-bridge breakage. And so we're going to follow ATP, ADP, and inorganic phosphate as we do this. So we can break this down into a 4-step cycle. So over here, top left is where we're going to start. Just to orient you up here, here is one of the heads, the myosin globular heads, and here is a thin filament. So we're zoomed in one of these regions in here. So here is our thick filament of myosins. Here's an individual myosin, and this is said to be in the cocked high energy state. Here is a thin filament. So a myosin head is going to bind loosely to the actin filament in its high energy configuration. So that cross-bridge formation, where we go from the myosin being cocked to binding the actin, that is now forming a cross bridge between the thick myosin filament and the thin actin filament. So this is a high energy state. And so when we release this inorganic phosphate here, that phosphate will come off in this second step, and that causes the power stroke to be initiated. And so that power stroke is going to be the elastic energy in the head, which was stored there from the hydrolysis of ATP, which is going to have occurred down here. And when we release that inorganic phosphate, the elastic energy in the head can be stored, and the cocked head of the myosin is going to pull. And so it's going to pull the actin filament away from the Z line. It's going to try and pull the actin filament away from the alpha-actinin in the Z line. And so if the Z line is over here and the actin filament is here, and we've got a head cocked here and we release that inorganic phosphate, we're going to be pulling that actin filament, and the Z line is going to come over with it, and so that's going to result in shortening of the sarcomere. Okay, so that's the power stroke there, and so the actin filament has been moved towards the center of the sarcomere. We're going to have a cycle now where we release ADP, we rebind ATP, and at some point we're going to make another association with the actin, but a little bit further down towards the Z line. And so at some point in here we're going to have some hydrolysis of this bound ATP, which puts the head into this cocked state. So the head here is in a relaxed state when it binds ATP. When ATP gets hydrolyzed, the head gets cocked back, then we bind tightly to our actin, we release the inorganic phosphate, and we pull the actin towards the middle of the sarcomere, towards that middle H region. And so what you can see is that the more heads that you have that can be forming cross bridges, the more powerful the contraction can be. And so all we're seeing is that we've got this cycle of ATP hydrolysis, phosphate release, ADP release, and that is all related to this process of cocking the head, attaching to actin, and then sliding the actin or pushing the actin and pulling that band towards the middle of the sarcomere. So what we'll look at next time is how do you actually control when this contraction happens, because you don't just sit having spastic contractions that you can't control. It's very carefully regulated. So we'll look at the role of nerve tissue that innervates muscle, and then how calcium is involved in regulating this whole cross-bridge cycle, and that means we'll have to take a look at the proteins troponin and tropomyosin on the actin filament. So I'll be back and we'll do that next time in Muscle Cells in Action 3. I'll see you soon.